Hello, we are Ilya, Christian, Alexandru, and Cosmin, and we are going to present our SBB route planner. The problem that we face is that Google Maps may just not be enough if we want to be sure that we get from point A to point B in time. Therefore, we propose another solution. Say we get some start and end station and the departure time, just like in Google Maps. Now we also receive as input the degree of certainty that our trip will arrive in time. Using this information, we want to give the user a safe route from A to B, returning the modes of transportation used along the way. For simplicity, in developing our solution, we only used the train, bus, and tram stations from a 10-kilometer radius from the Zurich train station. To begin with, we had to prepare our data in order to run the algorithms for this problem. We therefore started by filtering the stations in the SBB dataset to only get stations near Zurich. Then we organized the data in some relevant data frames, namely, a data frame storing the names of the stations and their identifiers, a data frame storing the edges of the graph formed by the stations and the connections between them, a data frame containing the schedule of the modes of transportation for a normal week, a data frame storing the walking times between close-by stations, and finally a data frame containing the delay distribution for each station and transport line pair. We have to mention that in building the timetable, we only used the last week of data available, as the schedules may change over time. After having prepared our data, we could finally start coding the real deal, the algorithms. Our first approach was to assume that all the modes of transportation would have no delays. In this case, the first step was to build an isochronous map. Namely, we ran a breadth-first search from the start station to compute the weights of the edges. The weight of an edge is computed as the difference between the arrival and departure times for the best connection found, plus the time that we have to wait to take that connection. After having built the map, the next step was running the Dijkstra algorithm to find the shortest route between the start and end stations in terms of time. For the full solution, where we also consider the possible delays, we start by running the deterministic planner. After that, we go through the best route station by station and compute the certainty of that route along the way. If at some point we find out that we have fallen below the desired certainty threshold, we stop and modify the cost of the edge we got at by considering the next connection that we can take for that edge. Afterwards, we run Dijkstra again and continue this way until we find a route that respects the certainty level. While writing the algorithms and getting routes in plain text can be fun, it is even better when you get to visualize your results on a map. For the visualization, we used the Google Maps API and created a split view with two maps. One of the maps presents the output of the basic deterministic planner, while the second one presents the output of the stochastic planner, where the colors are represented with blue for the ones that are most probable to reach and red for those that are less probable to reach. The visualization was developed using React. Having worked through the whole process, data preparation, algorithms, and visualization, it is time to draw a line and weigh the pros and cons of our approach. To begin optimistically, we can say that our solution is pretty straightforward and easy to comprehend, as it's just involved some basic data manipulation and classic algorithms on graphs. Speaking of graphs, finding the route with Dijkstra runs very fast, as the size of the graph is not so big. Last but not the least, using the latest data for the train, bus, and tram schedules is a plus, as we wanted to have information as up-to-date as possible. However, there are things that could have been improved. First of all, although the route planning itself runs pretty fast, the step of building the isochronous map could have been optimized. Second of all, when computing the walking time, we considered distance to be twice the straight line distance. We chose this approach because we could not use the Google Maps API for free for too many requests of this kind. Finally, to limit the computation, when computing the walking times, we only considered stations in a radius of 300 meters. This was our project. I hope you enjoyed it and see you in the QA session. Cheers!